Hi all, let's begin discussing series with section 10.2 in your book. So the first thing this section is going to talk about is infinite series. Now, an infinite series is just when we have a sequence, but all of the terms are going to be added together, thus making a series. So you'll see, I say an infinite series is the summation from n equals 1 to infinity of some general term a sub n. Now, because it's a series and a summation, then you're going to add each general term. So that when n is 1, you'd have a sub 1. When n is 2, you'd have a sub 2. When n is 3, you'd have a sub 3. So this infinite series is going to be the summation of a1, a2, a3, all the way up to a sub n as n goes to infinity. Now, this series is going to converge to some number L if we can say that the summation of this series of a sub n is equal to that number L. So in other words, all of these numbers have to add to be some finite value L. If that's not the case, we say it diverges. So it's either the sum is going to have some quantifiable finite value L for its sum, or otherwise it's going to diverge. If we can't say what it's going to, we just say it's divergent. Now, let's get some practice with series before we head into some more fun problems. So this first one that I'm wanting us to practice with, what if I give you the series of numbers 1 plus 1/4 plus 1 over 9 plus 1 over 16. So you need to be able to look at that and tell me what the series notation for that would be. So whenever you look at this, you'd say, well, the first term is just 1 over 1. The second term is 1 over 2 squared. The third term is 1 over 3 squared. The fourth term, 1 over 4 squared. So you can go back and say, well, I could call that first term 1 over 1 squared. So my numerator is always 1. My denominator is whichever term I'm in, the first, second, third, fourth term, it's that number squared. So I can say the general term, which is always referred to as a sub n, the general term of this sequence is 1 over n squared. Now, I can say the summation of the sequence, defined as s sub n, is equal to the limit as n approaches infinity of the summation from n equals 1 to n, as n goes to infinity, of 1 over n squared. And again, please notice that would give me all of this back. The first term, you'd have 1 over 1 squared. Second term, 1 over 2 squared. Third term, 1 over 3 squared, 1 over 4 squared. It would give me this forever and ever and ever. That's the quick summation way to write this series. Now, for a second problem here, if I have one like 1 over 9, which I know is 1 over 3 squared, and then the next one, 1 over 16, would be 1 over 4 squared. The next one would be 1 over 5 squared. The next one, 1 over 6 squared. So if I'm trying to find that summation, I could just say, well, then clearly, again, my numerator is always 1. My denominator, it's starting off with 3 squared, then moving to 4 squared, 5 squared, 6 squared. So if I have to start my summation at 1, then I would say, well, this is going to be 1 plus 2, this would be 2 plus 2, 3 plus 2, 4 plus 2. So I can say, how about I have that base of n plus 2 quantity squared? And then you can say, yes, okay, if that's my general term, 1 over n plus 2 quantity squared, then that's going to account for the first term being 1 plus 2, 3 squared, the second term being 2 plus 2 for 4 squared, 16, the third term being 3 plus 2, 5 squared for 25, and so forth. So I can say this summation is just from 1 over n plus 2 inside the series from 1 to n as n approaches infinity. Now, I wanted to note here, you don't have to always start your series at 1. It's still an infinite series no matter what finite value you started at, because you're still going to infinity. But in this case, the series that I have up here in this series are absolutely identical. They have the exact same number of terms, everything. So you say, well, this one's going to start at 3. Please notice, if I start at 3, although I do need to square that denominator, if I start at 3, my denominator is going to be 3 squared, that's the 9. If I go to 4, 4 squared is 16, 5 squared is 25, 6 squared is 36. So you could have just said, well, just start at the number that makes the series easier from the very beginning rather than worrying about how to make the inside what you need it to be. Those are two different ways of working the same problem. There's positives and negatives to each technique. Now, the next one. What if I have a series that's going to alternate in sign? So notice my first term's positive, second term's negative, third term's positive, fourth term is negative. So I need to be able to take care of that alternation in signs. So I'm thinking if I want to start at n equals 1, well, the first term has to be positive. When n equals 2, it has to be negative. Notice what I've done to handle the alternating sign. I said, well, alternating sign, we're just going to have negative 1 to a power. If I want to start my series at n equals 1, then I need to ensure that that first term is positive. I can do that by saying, well, negative 1 to the 1 minus 1 power would be negative 1 to the 0. We know by definition any number to the 0 power is 1, so it's going to make that first term positive. The second term, you'd have negative 1 to the 2 minus 1. You'd have negative 1 to the first. It's going to make that next term negative, and it'll make each other term after that alternate in sign. So I know that this is going to handle the alternation in sign. Now I need to handle the fraction. So as soon as I see those understood denominators, I have a 1, 3, 5, 7. You need to understand that those denominators, since they're going in increments of 2, you've got a multiple of 2 times n down there. Now, if it were just 2n, this would be 2, 4, 6, 8. You say, but it's not 2, 4, 6, 8. So you have to say, well, how about I subtract 1 in that denominator? Then when n is 1, you'll have 2 times 1 minus 1 is 1. When n is 2, 2 times 2 minus 1 is 3. When n is 3, 2 times 3 minus 1 is 5. It's going to give me every single one of those fractions that I need. So I can say, okay, then my summation formula is the summation from n equals 1 to n as the n approaches infinity of this general term. And what I've done with this general term is I just said, well, that negative 1 to the n minus 1 might as well just go up into the numerator of that general term of the oscillating sign. Now, in this next one, even better. So please notice here, your numerator. Whenever you see from the first term to the second term, hopefully you can see, well, that second term, it's just a multiple of 5 times that first term. So then I notice the first term, well, hey, that's 5 to the third power. This would be 5 to the fourth power, 5 to the fifth power, 5 to the sixth power. In my denominator, I noticed, well, this is 3 squared, 4 squared, 5 squared, 6 squared. So if you need the restriction that your summation needs to start at 1, then you think, well, okay, these are all just powers of 5. So this is going to be 5 raised to the 1 plus 2 power, so the n plus 2 power. When n is 1, this is going to be 125. When n is 2, this would be 5 to the 4th, 625. When n is 3, this is going to be 3,125, 5 to the 5th, and so forth. So I know I could call the numerator of the general term 5 to the n plus 2 power. Now in that denominator, the 3 squared, 4 squared, 5 squared, 6 squared, that first term being 3 squared, and I know if I need to start at n equals 1, then you just say, well, then that's 1 plus 2 to get to that first term. That'd give me the 3 squared. The next term n would be 2, so you'd have 4 squared. The next term n would be 3, you'd have 5 squared. It's going to give you all of that out. So I could just say my general term is 5 to the n plus 2 over n plus 2 quantity squared. And then the summation of the series can be that 5 to the n plus 2 over n plus 2 quantity squared. Now, you can also see here, I've went ahead and said that you could have started this series at 3. Since you automatically notice, well, this is just 5 to the third power. This is 5 to the fourth power, 5 to the fifth power, 5 to the sixth power. You could have said, let's let n start at 3, and then I'm just going to have 5 to the third, the next term would be 5 to the fourth, 5 to the fifth. That would handle the numerator. And again, your denominator would be handled because you'd have 3 squared, 4 squared, 5 squared. These two are the exact same summation. There is no difference in this and this. We can move from here to here or from here to here. Now, if I wanted to find the nth partial sum. So what I mean by that is, instead of saying S sub n is the sum out to the infinite term, let's say I want a finite sum, the nth partial sum. I want to find S sub 2, S sub 4, and S sub 6. If the function that this sum is referring to is the series from k equals 1 to infinity of negative 1 to the k times k to the negative 1. Now, keep in mind, you can use different variables for the indices. Typically, we see n, I, or k. They could be anything, though. So in this problem, I chose k. Now, the second partial sum, you say, okay, all that is you're going to add when k is 1 and when k is 2. That's precisely what I've done here. If k is equal to 1, you'd have negative 1 to the first plus 1 to the negative 1. That's where that's coming from. Plus the second term. Well, when k is 2, you'd have negative 1 squared plus 2 to the negative 1. Now here I've just simplified this. This is just going to be negative 1 times 1. So I get negative 1 for the first term. My second term I know is going to be positive because I have the negative 1 squared. And I'll have plus 2 to the negative 1 power is plus 1/2. Negative 1 plus 1/2, I can say S sub 2, the sum of the first two numbers is going to give me negative 1 over 2. Now, the next partial sum, we'd call S sub 4 the fourth partial sum. And in order to find that, you can say, well, S sub 4, it's just going to be S sub 2 plus the third general term plus the fourth general term. Well, S sub 2 we already know was negative 1 over 2. The third general term is going to be your relation on the inside evaluated at 3. So you get negative 1 to the third plus 3 to the negative 1. Plus the fourth term, negative 1 to the fourth times 4 to the negative 1. So that third term is going to give me a negative 1/3, whereas the fourth term is going to give me a positive 1/4. So now I have negative 1/2 minus 1/3 plus 1/4, and I'll get a total of negative 7 over 12 for that. So now I can say, okay, the fourth partial sum of this series, meaning the sum of the first four terms, is negative 7/12. Now if I say, okay, now I want to find the sixth partial sum. Well, that's the sum of the first six numbers. I know that the sum of the first six numbers is the sum of the first four numbers that we've already found, plus the fifth general term plus the sixth general term. So I already have the sum of the first four is negative 7 over 12. The fifth general term, negative 1 to the fifth times 5 to the negative 1, plus the sixth term, negative 1 to the sixth times 6 to the negative 1. That fifth term is going to give me minus 1/5. The sixth term is going to give me plus 1/6. I just entered that into a calculator and I simplified it to a fraction, negative 37 over 60. So you're thinking, well, okay, that's not too bad finding the nth partial sums for these. It's really not. Now, if I wanted to go on to another topic, and this topic extremely important, it's going to be carried on through every section in the remainder of chapter 10. It's called the divergence test. Now, something I'm wanting you to remember with the divergence test, it goes with the name. The divergence test can only tell you if a series diverges. It can never tell you if something converges. It only tells you if something diverges. Just because it doesn't necessarily prove something diverges doesn't mean it converges. Okay, so divergence test. It's just saying that the limit as n approaches infinity of that general term inside your series cannot equal 0. Now, I should say, if the general term does not equal 0, then the series diverges. Make sure that makes sense to you. Please think about that. If it's not equal to 0, then that means you're adding an infinite number of non-zero terms. Well, if you're adding an infinite number of non-zero terms, clearly it's going to diverge. You can't add infinitely many non-zero terms. So it's saying if that limit as n approaches infinity of the general term is not 0, then your series will diverge. Period. End of story. Now, what if the limit as n approaches infinity of the general term is 0? That is not conclusive evidence that your series converges. So in that case, we just say, well, the divergence test is inconclusive. Your overall series could converge or diverge. But the main point, and again, since I stumbled when I was first saying it, let me go back to this right up here. The divergence test is telling you that if you try to take the limit as n approaches infinity of the general term in your series, and you can't show that that's equal to 0, then automatically what you have shown is that that series diverges. Now, just because you show it's equal to 0 doesn't mean it converges. In that case, it could converge or diverge. Let's look at an example of that. And in this case, I'm going to go ahead and say this series diverges. Show me why. So show why the series n over the square root of n squared plus 1 diverges. And please remember, anytime you don't put limits on your summation, it's automatically meant to be 1 to infinity. So this is the series as n goes from 1 to infinity of n over the square root of n squared minus 1. Now, so I can go in and I can say, well, then that general term a sub n, it's just the term inside that. If I take the limit as n approaches infinity of that general term, then I'll say, well, it's the limit as n approaches infinity of n over the square root of n squared plus 1. I've went ahead and done an algebraic simplification to this limit, and I said the degree of the numerator and denominator are both degree 1. But remember, whenever you divide by degree 1 inside of a square root, the square root of n squared is equivalent to n. So inside the square root, to divide by degree 1, you've got to divide by an n squared, since the square root of n squared is n. So I went through and I divided by n squared into both terms inside the square root. I did the same thing in the numerator. I divided by n. That allowed me to see that this limit as n approaches infinity simplified down to be 1 over the square root of 1 plus 1 over n squared. At that point, you can very easily see what your limiting value is. If you allow n to go to infinity, any finite number divided by an infinite number goes to 0. So you're going to have 1 over the square root of 1 plus 0. That's just 1 over 1. You get your limiting value of 1. Now again, you can say, okay, what does this mean? It means you're going to be adding an infinite number of non-zero terms, which means your series diverges. So that's what I'm saying right here. Since the limit as n approaches infinity of the general term is not equal to 0, in fact in this case it was equal to 1, then your series has to diverge. So I'll say this series diverges because the limit as n approaches infinity of the general term was not 0. Nice. Now if you want to see an even nicer problem, I love these because it brings back a concept that we talked about back when we were integrating in Chapter 7. So sum of a telescoping series. A telescoping series is whenever you have a factored denominator. So if I have the series from n equals 1 to infinity of 1 over n times n plus 2. So I've went ahead and I've written out the first 4 terms of that series. So notice, when n is 1, you'd have 1 over 1 times 3. That's going to be 1/3. When n is 2, your denominator would be 2 times 4. Your fraction would be 1/8. When n is 3, you'd have 3 times 5 for plus 1/15. When n is 4, your denominator would be 4 times 6 for plus 1/24. So now, if you just look at this, you can say, well, clearly this fraction is going to get smaller and smaller and smaller and smaller. So yeah, the limit as n approaches infinity of the general term, it is going to go to 0 because this term is going to become 1 over infinity times infinity plus 2. Clearly that limiting value is 0. Now that doesn't necessarily mean it converges. So right now, if I just think about the divergence test would tell me that this could converge or diverge. But now my goal is to show that it does converge. So I would ask you to algebraically look at that 1 over n times n plus 2, and you can say, this is the method of partial fractions. Gorgeousness. and we say, well, I'm going to call it a over the linear factor n plus b over the linear factor n plus 2. And then I can break it up and say, well, if I take this equation and multiply by n and n plus 2, my left-hand side is going to be 1. My right-hand side is going to be a times n plus 2, and then I would have b times n. In order to solve that, I would just go in and say, well, how about I let n equal 0, and I should be able to solve for a. If I allow n to equal 0, my left-hand side is still 1. The b would cancel out on the right-hand side because it would be multiplied by 0, and the a would be multiplied by 2. That's where this is coming from. 2a would equal 1. Therefore, I know a is 1/2. Now, if I allow n to equal -2, it should cancel out the a term here. Meanwhile, the left-hand side, it's still going to be 1, and you would have b times -2. So I'm getting -2b is 1, divide by -2, you've got b is -1/2. Now I know what a and b are both equal to, so I'm going to come down here and say, well then this original series that I was dealing with, I know I can call it 1/2 times the group of the series, where now if I factor out a 1/2 out of that, then a over n, that's just going to be 1 over n, and then I need to subtract because b was negative, but I factored the 1/2 out, so you just have minus 1 over n plus 2 here. Now, at this point, you may not think that this is any better than what I started with, but oh, it's so much better, because what I started with, I really didn't know how many of those numbers I was going to have to sum before I reached any value of where the limit was going to. Now it's going to be very, very, very easy to see. Let me show you. So I have 1/2 times the summation of these series. So I bring the 1/2 down, and I just start thinking, instead of listing out the terms like that, let's list out the terms in expanded format. So if I plug in n equals 1, then I'll get 1 over 1, which is just 1, minus 1 over 1 plus 2, which is 1/3. So I have, the first term is going to be 1 minus 1/3. Please do not simplify that down to be 2 over 3. Now, and please notice, 1/2 times 2 over 3 would give you back the first term you have up here. It's much better to think of it like this, though. Now, my next term, the second term, well, when I plug an n equals 2 in here, I would have 1/2 minus 1/4. The third term, 1 over 3 minus 1 over 5. Now, hopefully, and you might see, why didn't I do any other terms? Because I know every single solitary other term, its terms are going to cancel out. How do I know that? Please notice, the first term in my next one would be plus a 1 over 4. Well, that's just going to cancel with that minus 1 over 4 right there. And I know that this positive 1/3 cancels with this negative 1/3 here. So every single first term is going to cancel out, with the exception of the first two. You can never subtract a number of 1/2 or 1. The largest number you're subtracting is minus 1/3. Now on the other end, if you think about what's the term preceding this one right here, it would be 1 over n minus 1 minus 1 over n plus 1. So while you can't ever cancel out the first two terms, you're not ever going to be able to cancel out the second terms of the last two terms. So I would have minus a 1 over n plus 2 that never cancels out. The term preceding this, I would have a minus 1 over n plus 1 that would never cancel out. The term preceding that, the minus 1 over n, would cancel with this 1 over n. So I'm coming down here and saying, well then this summation is going to equal 1/2 times the limit as n approaches infinity. What's the only terms that will never cancel in this case? 1 plus 1/2. And then these really become irrelevant, but I went ahead and put them minus 1 over n plus 2 minus 1 over n, minus 1 over n plus 1 minus 1 over n plus 2. Why did those last two become irrelevant? Because you're taking the limit as n approaches infinity. So does it really matter if you're subtracting off minus 1 over infinity minus 1 over infinity? Nope, those values go off towards 0. So we say our limiting value is just 1/2 times the group 1 plus 1 over 2, and you'd get your 3/4 here. Now, just for fun, I wanted to go to the calculator and show you, you could kind of check this, although these are really tough to show on the calculator, but I'll try to do it here with you. If I go math, I want to do a summation, and I'll just let x be my variable. It makes it easier. So I'll say, let's go from 1 to 500. Now, clearly, that's not going to infinity, but your calculator would just sit there and spin and just take way too long if I choose any value greater than 500. And I know I have a fraction on the inside, 1 over x times x plus 2. So this is going to be the sum of the first 500 terms of this series. So I'm getting 3/4 here for the sum of all infinite terms. Now, I know the sum after the first 500, you're adding a negligibly small value anyway. So please notice this is a good way to double check, and you say, well, these two numbers should be relatively close. Well, they certainly are. 0.748, so it's just saying you only accumulate 0.002 approximately for the summation of numbers 501 to infinity of the rest of this function. So the numbers get extremely small after the 500th term. Now, next up, you're like, well, okay, we've looked at general series notation, then we summed some series, then we looked at the divergence test and the telescoping series. The last thing in this section I want to talk about, and it's probably the most important, is the geometric series. So the geometric series is when we have some constant starting off, and the constant could be a 1, it doesn't matter, c could be any number, but then every successive value after that is multiplied by some common ratio. So I'd have c plus cr plus cr squared plus cr cubed plus on and on and on. Every term thereafter has an additional factor of r. Now, if I wrote this with a summation starting at 0, and I think it's kind of nice to start it at 0 because you say, well, r is understood to be to the 0 power initially, then you could just say this is c times r to the n for n equals 0 to infinity. Now, a lot of our summations don't start at 0, but rather they start at 1, so that's no big deal. If you wanted to start this summation at 1, you could say, well, then c times r to the n minus 1 power. Notice, if n is 1, then r is to the 1 minus 1. You start off with r to the 0. These two are the exact same summation formulas. One is really not better than the other. Now, what we need to do is be able to have some formula that can find the summation of any convergent geometric series. And you'll see I've already put, when I say it's a convergent geometric series, I'm saying r has to be some value in between -1 and 1. Or in other words, we can say the absolute value of r needs to be less than 1. And that should automatically make sense to you. Why should it make sense to you? Well, think about it. If r is not less than 1, like if the absolute value of r is not less than 1, what if r is 1.1? Then each term of your series would be getting larger and larger and larger and larger. Even if it were negative, the absolute value of each term of your series would be getting larger. It would just be an alternating sign. And in that case, it would fail the divergence test, because the divergence test says that your series only, that if the limit as n approaches infinity of the general term, if that's not 0, then boom, it diverges. Well, if the absolute value of r is greater than 1, then that a sub nth term as n approaches infinity is certainly not going to go to 0. It's going to go off to some enormous value. So we have to have values of r in the geometric series between -1 and 1, or we say the absolute value of r is less than 1. Now, when I'm looking at how to find this sum of a geometric series, I'm wanting you to think about this with me. I'm saying, okay, the sum of a geometric series would be the constant plus the constant times r plus the constant times r squared plus the constant times r cubed, all the way to the constant times whatever r to the n power is. Now, I've went in and then said, well, okay, now what if I take this entire equation and multiply by the r value? So your first term is CR, second term CR squared, third term CR cubed, all the way to the last term of CR to the n plus 1 power. Now the goal is to try to solve for S sub n as a nice function. So what I've done is I've said, well, let's take what we did for the sum of the first n numbers and subtract from it r times the sum of the first n numbers. And you can see almost everything is going to cancel out. All of these terms will cancel with all of those terms, with the exception of you're not going to have the constant in the first equation cancel out, and then you're going to have minus the very last term in your second line. So I have c minus c times r to the n plus 1 power. Now, my goal is to solve for s sub n. So I factor out an s sub n on the left-hand side, and you can say, well, that's going to be s sub n times 1 minus r is equal to this c minus cr to the n plus 1 power. And then s sub n is going to equal what I had on the right-hand side. The only thing I've done from this step to this step is I factored the c out, and I had times the group 1 minus r to the n plus 1. We divide that by what was previously multiplying s sub n, the 1 minus r, and then I can say, okay, now this is my formula for s sub n, but now I need to remember this formula is supposed to represent an infinite sum as n approaches infinity. So as n approaches infinity, the only value in this problem that impacts is this value of r right here. There's nowhere else where n is on. And then you say, yeah, but in order for this to converge, we've already discussed r has to be an absolute value less than 1. So it has to be a value like 0.9, 0.99, negative 0.99, negative 0.1. Any of those values of decimals, if you take that value to an infinite power, it's going to go off towards 0. So you'll notice what's happened from here to here. I'm just saying, since the absolute value of r is less than 1 and it's raised to an infinite power, that whole term becomes 0. So my entire numerator is just c times 1, which is c. Now your r did not disappear in the denominator. It's not raised to the n power, so you have c over 1 minus r. So we can say the infinite sum of any of these geometric series is just whatever the first term of the series is. C is always the first term, divided by 1 minus the common ratio. Now, let's do that in order to find a sum. So I'm saying let's let s sub n equal the infinite series of 5 plus 5 over 2 plus 5 over 4 plus 5 over 8. I'm wanting you to add the infinite many terms in that series. Of course, that keeps on getting smaller each term. My next term would be 5 over 16, then 5 over 32, and so forth. So you're supposed to analyze from that and say, well, okay, your first term is 5. Your common ratio, after that first term, each term is successively multiplied by an additional factor of 1/2. So r is 1 over 2. The sum of this series is going to be the first term divided by 1 minus r, 1 minus 1 over 2. At that point, I just simplified this by multiplying by 2 over 2. I wanted to get rid of the fraction in the denominator. Gives me a 10 in the numerator. My denominator would have been 2 minus 1, which is obviously 1. The sum of this series, so if you added up all of those terms, infinitely many, you're just going to stop at 10. Now, one in which you should not, and this is a case where I see a lot of students made a mistake, so I wanted to draw your attention to what I've done here on number 9. In number 9, I'm asking you to do the summation from n equals 0 to infinity of pi over e to the n power. So then you'd say, okay, then my constant term, or my first term, the constant would be pi over e to the 0 power. We know any number to the 0 power is 1. Every term after that is constantly multiplied by yet another factor of pi over e. So my r value would be pi over e. Now, I went ahead and did it here just to show what I see students do all the time, and we'll talk about how you know that that's not right. But I should have known not to do this in the very beginning. How? Well, because look, pi over e. Pi is 3.1415, e is 2.7182818. So we know that that ratio is greater than 1. It's going to diverge. Period. End of story. This will not converge to some nice number. Now, the way that you know that your answer over here is wrong, if you try to put it into your function, notice it'll allow you to put it into the function, but you're going to have to use logic to know that the answer is wrong. So I would say, well, it should be your first term over 1 minus r, which I can do. I could even make that fraction look nice by multiplying by the denominator of e. So I multiply by e over e. My numerator would be e. My denominator would be e minus pi. but then I notice e minus pi, that's going to give me a negative in the denominator. E divided by e minus pi ended up being a negative 6.42. Now, that should automatically catch you off guard, because look at this. This is a function with a base of pi over e raised to a positive power. You can never have a sum of positive bases to positive powers and get a negative. That should automatically just send off red flag and say, nope, that cannot happen. My first term would be 1, my next term would be pi over e, my next term would be pi squared over e squared, my next term would be pi cubed over e cubed. You can't take a sum of positive numbers and get a negative. Well, that's because that this formula is not relevant if it's not a convergent series. This series is not convergent. So that's why I put up here that this is not valid. Remember, this is only valid if the absolute value of r is less than 1. So instead of all of this, you would say absolutely not. Do not answer that. Instead, you just say S sub n in this problem diverges, because the r value was greater than 1. Now, let's look at the reciprocal of that geometric series. I said, well, what if I put e over pi? That should be no problem. That's a number less than 1. The summation of e over pi to the n, my first term would be e over pi to the 0 power. Any number to the 0 power is 1. Your common ratio is e over pi. So then my summation formula says it's the first term 1 over 1 minus r, which is e over pi. I multiplied by pi over pi to simplify. Your numerator is pi. Your denominator would be pi minus e. And I went ahead and got an approximate answer to that of 7.421 there. So we can say, well, okay, that one certainly realistic. That is the answer to this geometric series that converges. And I know it converges because the absolute value of r is less than 1. I wanted to look at one that I think would cause even more confusion. So in this one, what I have is the sum of two geometric series. You cannot leave those together. So automatically, when I have the summation from n equals 0 to infinity of 3 times negative 2 to the n plus 5 to the n over 8 to the n, you'll notice I went ahead and broke it into, well, I can say this would be my first series, and then this would be my second series. In this first series, that 3 is not raised to the n power, so I just left it out in front, and then I said, well, I would have negative 2 to the n divided by 8 to the n. I might as well just say that's negative 2 over 8 to the n. Negative 2 over 8 reduced down to negative 1/4 to the n. So now I can look at this series and say, okay, what's the first term of this series? Well, when n is 0, the first term is going to be 3 times 1. Your first term of this series will be 3. And your common ratio is going to be negative 1/4. Now my second series came from this portion right here, the 5 to the n over 8 to the n. I just said let's add the separate series, 5 over 8 to the n. And the first term of this series would be 5 over 8 to the 0 power, which is 1. So now please notice I said the summation is the summation of the first, and you have to do these separately. The summation of the first series, 3 over 1 minus r, 1 minus a negative 1/4. R can certainly be negative. As long as it's not less than negative 1, it's going to converge. And then I say plus, the second series had a first term of 1, and then I would divide that by 1 minus r. Clearly r is your 5/8. So now in the first one, all I've done from this step to this step is I multiplied by 4 over 4. That gave me a 12 in the numerator and a 4 plus 1 in the denominator. The second one I multiplied by 8 over 8, and I got 8 over 8 minus 5. So my first one is going to be 12 fifths. My second one is going to be plus 8 thirds. 12 fifths plus 8 thirds gave me 76 over 15. So I can say this glorious series that goes to infinity of the sum of these two geometric series within has a sum of a rather small value, like that's what, 5 and 1/15, a little bit greater than 5, like 5.06 repeating, 76 over 15. Pretty cool that an infinite sum of something that looks confusing like that could have such a nice answer there. Now, the next section will be looking at more summation formulas and different types of convergence and divergence tests in 10.3.